When we think about our genetic code, we usually picture a simple sequence of letters, A, T, C, and G. But today, we're going to look a lot closer. We're going to see that these aren't just letters. They are incredible, masterfully designed molecules where literally every single atom has a purpose.
So let's start with a design challenge. Imagine for a second that you were tasked with creating a molecule, one that could store, protect, and transmit the instructions for every single living thing on Earth. What properties would it even need? You see, the genetic code is like this vast chemical library, and the real brilliance is in how the letters themselves, the nitrogenous bases, are built to meet this unbelievable challenge.
So our first stop is to look at the basic architecture. How do you even begin to design a chemical alphabet? Well, it turns out nature started with just two fundamental shapes. And here they are. Over on the left, we have the purines, which have this larger double ring structure. And on the right, you've got the pyrimidines with a more compact single ring. The entire genetic language, the whole shebang, is built from these two simple complementary forms. And that size difference? Totally not an accident. In fact, it's about to become incredibly important. Okay, so let's put some names to those shapes. Our two purines are adenine and guanine, A and G. And our three pyrimidines are cytosine, thymine, and uracil, C, T, and U. Now, what's really interesting is that DNA and RNA use a slightly different alphabet. DNA uses thymine, but RNA swaps it out for uracil. And just look how similar they are. The only difference is that tiny little methyl group on thymine. A tiny change with a massive purpose that we're about to explore. Okay, so we've got our letters, but a library isn't just a random pile of letters, right? You need grammar. There have to be rules that dictate how they connect to form stable, readable sentences. So let's see how this works. The number one rule of this genetic grammar is hydrogen bonding. These are basically weak attractions that form between the bases, and they're incredibly specific. As you can see, the molecular shape makes sure that adenine always pairs up with thymine and guanine always pairs with cytosine. This is not random. It's a precise chemical lock and key system, and it's what ensures our genetic information gets copied almost perfectly every single time. But here's the thing. Not all pairs are created equal. The adenine-thymine pair, AT, is held together by two hydrogen bonds. The guanine-cytosine pair, GC, on the other hand, is held together by three. So the crucial point here is that the GC bond is way stronger. It's like a tougher lock to pick. And this isn't just some minor chemical detail. It has huge biological consequences. And this right here perfectly illustrates that consequence. This graph shows what's called the melting temperature of DNA. That's the point where the two strands get pulled apart. Just follow the blue line. That's our GC-rich DNA. Notice how it holds together at much higher temperatures than the red, AT-rich line. It just takes more heat, more energy to break those three strong bonds. That's absolutely critical for organisms that live in extreme environments, making sure their genetic code doesn't literally fall apart. Now, there's a second major force at play. The bases themselves are flat and hydrophobic, which is just a fancy way of saying they hate water. So inside the watery world of the cell, they do something really clever. They stack on top of each other like a neat pile of plates, tucking themselves away from the water. This base stocking creates a dense, stable core for the DNA helix, protecting all that precious information that's held inside. Okay, so we've built a stable library, but what happens when the ink starts to fade? The genetic manuscript is under constant attack. So how does life protect its most important document from being corrupted? Right. Our DNA is not invincible. It's constantly being attacked by chemicals, by radiation, even just by spontaneous decay. One of the most common threats is something called deamination, the spontaneous loss of an amino group. If these little changes aren't corrected, they become mutations, permanently corrupting the blueprint of life. Let's focus on one of the biggest culprits. This is cytosine, our letter C. Over time, just through natural chemical processes, it can lose an amino group, and poof, it spontaneously turns into uracil, or letter U. Now, this is a huge problem. You now have the wrong letter in your genetic sentence, and this brings us to a really fascinating molecular mystery. The cell has these repair enzymes that are constantly patrolling the DNA, looking for errors. But if this little repair enzyme finds uracil, it faces a critical question. Was this uracil meant to be here, or is it a mutated cytosine? Since uracil is a perfectly good letter in RNA, how on earth does the DNA repair system know it's an imposter? And the solution? Oh, it is just absolutely elegant. Remember how we said DNA uses thymine instead of uracil?
Well, look closely. The only difference between them is this single, tiny methyl group. That's it. 1 carbon and 3 hydrogen atoms. So what's the big deal? Well, that little methyl group on thymine acts like a chemical tag. It essentially screams, I belong in the permanent DNA library. By using thymine as the official partner for adenine, the cell establishes a very simple rule. Any uracil found in DNA is, by definition, in error. It has to be a mutated cytosine.
And here we see the whole system in action. A C mutates into a U. The repair enzyme spots that untagged uracil, knows it doesn't belong, snips it out, and replaces it with the correct cytosine. A potential mutation is transformed into a clear signal for repair. It's an ingenious, self-correcting security system that's built right into the letters themselves. So let's just take a step back for a second and appreciate the big picture. When you put all of these features together, you don't just have a collection of molecules. You have a true masterpiece of chemical engineering. So let's bring it all together and recap the key design principles we've just seen. First up, those flat planar rings. They're perfectly shaped to stack tightly and create that stable core. Second, the precise placement of atoms for hydrogen bonding. That's the grammar that dictates the AT and GC pairing rules, making sure our code is copied correctly. Third, the hydrophobic nature of the bases is what drives the whole structure into that protective helix. And finally, that elegant little detail, thymine's tiny methyl group, the built-in tag for the cell's arrow-proofing system. You see? Every single feature serves a critical function. So the next time you see that simple string of A's, T's, C's, and G's, remember what you're really looking at. It's not just an alphabet. It's a purpose-built molecular system, where in the truest sense, form doesn't just follow function, it defines it.